Okay, quick break. We're back. This we're staying with assignment 2 here, and we had by popular demand. We're going to take a look at this problem number 3. This is true. I actually had some pals make a hot tub they used out camping. They didn't quite do it this way, but I was pretty amazed at those guys. Did it on wheels and all 9 yards. So we've got a hot tub at our campsite. We're just going to use the campfire, okay, fire, and we want to determine our energy use, so we referred to box 5.6 for help. So we got box 5.6, and I think that's on boiling water right there. And instead of boiling 500 gallons, they're boiling, I think, a kilogram of water, if I remember right. What page is that thing on?
167.
Yeah. Let me go find that. Oh, I'm way off. Page 167, box 5.3. Yeah, they're boiling 1 kilogram of water. The hot tub contains 500 gallons of water, so we're gonna get wet. And the water temperature was 45 degrees Fahrenheit to begin with. On its first use, we lost track of our campfire hot tub, and the water started to boil. How much energy did we expend? Okay, so let's get this up and do this the right way this time. Maybe. Yeah, maybe not. Let's go here. Come on, guy. Where'd you go? There it is. So this is problem 3. Assignment 2. So we gotta find energy required as megajoules to bring this thing to a boil. Where'd you go? Here it is. And it's given, it's 500 gallons of water. The temperature to start with, should we call that T1? 45 degrees Fahrenheit, the water temperature. What else are we given? Is that it? Yeah, that's all we got. Oh, man. What temperature does water boil at in standard conditions? 212. Yeah, you guys own that. So, second temperature, the boiling temperature, is 212 degrees Fahrenheit. Well, we can solve this. However, we need a conversion, don't we? And we need to know how to do this. Well, from box point 3, we can calculate energy as the mass of the water times the heat capacity of the water. I think that's C sub P. The specific heat capacity of the water times the delta T. All right. So we got the temperatures, we can get the delta T, we got the gallons. We don't have mass, but we can calculate mass from volume, right? We don't have the heat capacity. What's the heat capacity of water? Well, it shows in box 5.3, or you can go to your appendix and find what that is. What is the heat capacity of water? It's in the first line of box 5.3.
4,200 joules.
Yeah. 4,200 joules. What is that? Per kilogram. What's K? Degree Kelvin. Okay. Per kilogram, degree Kelvin. And I know you've had this when you looked at Carnot efficiency. 0 degrees Kelvin is equal to minus 273 degrees Celsius. Okay. And the section on Carnot efficiency states also when you're dealing with degrees centigrade and you're dealing in differences, the 273 cancels itself out. You got it? I'll show how we can do that. All right. So we've got heat capacity. What kind of units are these? These are metric units, aren't we? Well, I don't deal in metric in my head, but it's 500 gallons of water. I got an idea how much that is. So many kilograms of water, I don't. So that's why this problem is presented. Same with temperatures. So I'd suggest we convert these English units we're given to metric and then solve the problem. You could convert the 4,200 joules per kilogram degree Kelvin to a English unit heat capacity, but the text all the way through solves these in metric units. Okay. Plus, that conversion it's just like doing the problem. You might as well start from the other way. Okay. So, who knows how to convert degrees and without Googling it, knows how to convert degrees. You Google the method, but don't convert degrees Fahrenheit to Celsius. I'll tell you an easy way. Okay? It's an easy one to remember.
273 plus the...
No, that's Kelvin. That's centigrade and Kelvin. Okay? We're given this temperature, first of all, is 45 degrees Fahrenheit. Well, let's convert degrees Celsius because our...
Oh, Celsius.
Yeah. Well, it's a good question because it's kind of confusing. This formula deals in delta T, so we're dealing in differences of temperature, which means the 273s cancel out in both cases, and I'll show you how that works once you get to Celsius. So you don't need to worry about the Kelvin. When you're dealing in differences, this C sub P can be per degree centigrade. Okay, if you're dealing in one temperatures per Kelvin. All right. Okay, and I didn't explain that very well, did I? I put my hand down the wrong place again. Okay, so I like this. Degrees. Where'd it go? Fahrenheit. Oops. Is equal to 9/5 C plus 32. All right? At 0 degrees Fahrenheit, or 0 degrees Celsius, that's freezing, standard conditions, which is 32 Fahrenheit. It's a good way to remember that. At 100 degrees Celsius, that's boiling, the standard conditions, 212. That's one way you can check yourself. But we want to convert the other way around. We want to go from Fahrenheit to Celsius. So this formula doesn't work without a conversion. But I can remember this formula all the time. And it's one worth remembering. It's not top of your head. Because I'm reading something in the book and they're talking about 20 degrees Celsius. That doesn't mean, I don't know how to deal with that. Well, 20 degrees Celsius is, put the 20 in there, 4 times 36, about 68 Fahrenheit. So they're talking 20 degrees Celsius as a typical indoor home temperature, 68 degrees Fahrenheit. Okay. It's handy, helpful to have a little bitty conversions you can call upon pretty quickly between metric and English, particularly with this text. Okay. So let's do some algebra. Who's good at algebra? Huh? Let's solve for centigrade. Well, what can we do? We can subtract 32 from both sides, can't we? We do the same with the both. Okay. So F minus 32 is equal to 9/5. I better do that one. C plus 32 minus 32, right? We subtracted 32 from both. So I got the 32 out of there. right? So F minus 32 is 9/5 C. You with me? Let's go up here. Hopefully I can do it. So now we're at 9/5, and I'm going to write it on the other side. C equals F minus 32. Right? We want to solve for C. How do we do that? We can get C to unity by taking C times what? Yeah, 5/9. You got it. So we take 5/9 times both sides. Voila. We got it. Those cancel. Degree centigrade is 5/9 over F minus 32. Okay. So in our case, the starting temperature as centigrades is 5/9 of 45 minus 32. I think it's about 7 or something. I gotta find my.
Yeah, that's 7.222.
Yeah, all right, let's call it 7.2 for this. And then the ending temperature, we know what that is. That's 100 Celsius. But let's test our formula, right? 5/9 times 212 minus 32. What does that come out? That'll come out to 100. Yep. Geez, that's written poorly. Got it? So that's our given now becomes, and I want you, when you do these problems, show how you got there. Yeah, I had a guy that wasn't not too far out of high school in both 101 and 102, and I don't know if he ever read the book. I don't know. He struggled. He finally was getting it better in 102, but even on tests, my word, he wouldn't look at the book. He'd Google stuff. Like, he did okay at times, and times to come up with get off track. Yeah. So, be able to figure it out on your own. Be able to do some of that. Okay. So now we've got, for a starting temperature, 7.2 degrees Celsius, and we're ending at boil at 100. Okay, we got that part done. Now we got 500 gallons of water. We don't have mass. We need mass, okay. However, we can convert that. Because we know in standard condition what water weighs. What does water weigh in standard conditions? I think it's 8.33 pounds per gallon, right? Yeah.
Heavy.
It's heavy. You got it. It's amazing, isn't it?
Maybe it would be more, maybe like 8.7.
Carry a 5-gallon bucket around all day, times 8.33 pounds per gallon. So now we got it in pounds. We want to get it to kilograms. How many kilograms per pound? We did that last week. 0.454 kilograms per pound. So that gives us how many kilograms? Whoops. Let me look at this and find it. Let's pause this for a minute. Make sure I'm on the right track here. I'm pretty sure I am. What are we doing here? We're doing good. We got a prod 1900 or 1890. Oh. There we are. Kilograms of water. Now we can roll on this formula because our C sub P again is in metric units. So the heat is equal to the mass. So we took the volume of water, because we knew the density, standard conditions. We got 1,890 approximately kilograms of water. Our next thing was the C sub P. Is that how we did this? MC sub P, which is 4,200 joules per kilogram per degree Kelvin times the difference in temperatures. And how should I do this? It's 100 degrees centigrade plus 273, or minus 273, excuse me, I do that every time. Minus 273, yeah. Minus the 7.2 degrees Celsius. Okay, that didn't do units, Celsius, degree, Kelvin, degree Celsius, minus 273 Kelvin. And this is what I was talking about before, Todd. The 273 cancels out, right? So you got a minus 273 minus a minus 273, they cancel out. So when you're dealing with differences in degrees centigrade, it's the same, or degrees Kelvin, it's the same as degrees centigrade. Now if you're looking at the heat of the volume of that water once it gets there, that with the heat capacity you can't do that. But okay, so that cancels out. What does that come out to be? Approximately, whoops, what else we got wrong here? We want the answer in megajoule. Well, we can do it in joules. Let's convert it right here. 1,000 joules per megajoule, is that correct? And you're going to want to show those units in doing this. And it comes out to approximately, it's like 737 megajoules of energy. We've done the first part of that problem. Okay? So it took 737 megajoules of energy to bring that water from 45 degrees Fahrenheit to boiling. Okay? Now, that's not too tough. In 102, I go on to have them calculate at a certain campfire efficiency how much wood that is, given a certain size log. How many logs did you have to throw in there? It got pretty funky, yeah. Relatively easy, but again, I gave the volume of the log, or the dimensions of the log in English units, so you had to convert, and it got a little funky. Okay, second part of this problem. And I got to look at this thinking, well, maybe you haven't had this yet. Part two of the problem. Bonus question. No, it's not part two. It's a bonus. I got really cheesy the next semester. I made it a bonus rather than being part of the problem. Man, too wussy. Okay, we were distracted long enough, and off camera I'd say drinking beer, that 5 gallons of water boiled away. As we were distracted, my feet got cold. If we were able to collect the steam that boiled away and condense it, is an important part of this, to provide us some heat, how much energy would we retrieve from just the steam condensing? Now your University of Montana campus, much of which is heated by a gas-fired, it should be wood, I won't go into that, gas-fired steam boiler, superheated steam. Remember what superheat is? Do you have that yet? Superheated steam is that steam heated well past the boiling point, okay? And we have superheated steam at the mill. And the superheated steam, the advantage to that is if you're transporting that steam over distance, you lose a lot less heat. If you're transporting that steam near the boiling point, near saturation, you're going to have a lot of it condense out the sides of the pipes, even though if they're well insulated. Anyway, so that steam is transported to various buildings around campus into radiators. So what do the radiators do? They condense that steam and give off heat, just like an old home with the radiators. Okay. So what in the world is that term? How much energy would, well, it's box 6.2 this. You guys are in chapter 6. How topical. If we were able to collect the steam that boiled away and condense it to provide us some heat, how much energy would we retrieve from just the steam condensing? The latent heat of condensation. Well, let's fire off to box 6.2. What page is that, guy?
181.
181. I'll clear over here in electricity, because I like it so much. Okay. Thank you. 181, box 6.2 relates to this problem. In this problem, they're talking about the latent heat of vaporization. The latent heat of vaporization is that heat required to boil water away, okay? Once you've reached boiling, it's a different ballgame. You're in a different phenomena, and it takes a lot more heat to evaporate that water off, okay? You've got your coffee in a mug and you're heating it up and it comes to boiling. Well, that's too hot to drink. You don't want to do that. But if you do and you forget it, the volume in your cup goes down. The latent heat of vaporization is the energy required to drive that water off and bring that volume down. You're getting more coffee. You're getting stronger coffee for sure, as we know. Okay. And the opposite is true, and that's the latent heat of condensation. When you've got superheated steam, okay, so if you were to, when you boil that coffee and you let it on there too long, if you were to collect that vapor that came off that coffee and condense it again, you'd get that heat back again once it condenses, okay? That heat comes back into that water or that coffee. So, in this case, we're going to use it to warm my feet. Well, how much if we let 5 gallons of that 500-gallon hot tub boil away, how much heat would that be? And megajoules, probably, it doesn't say how much energy you would retrieve. Well, the key component there is what's called the latent heat of vaporization. For water, and it says right in that box, the heat needed to convert 1 kilogram of water at 100 degrees centigrade into steam at that temperature is 2.258 megajoules per kilogram. Well, let's write that one down. If I can get there. Don't want that one. So, part 2 or the bonus. Got it? There we go. You got 5 gallons of water, boil away. How much energy is that if you were to condense it? And it's the same amount of energy whether you're boiling it away or condensing it again. I use that condensing again as an example. Okay. So your important parameter there is, again, the latent heat of, in this case, let's stick with vaporization. We're going to calculate what that is to boil away. Or when you're bringing it back, condensation. Which we just stated as given in your text, another important parameter, 2.258 megajoules per kilogram. Now, my old days at learning, trying to graduate in chemical engineering, I'd go through this whole problem again. I'd be converting that 5 gallons to, what do you want to convert that to? A mass as kilograms, right? But maybe a long time later, we got smarter. We've already done that. What did we just do? We took 500 gallons of water and found that was, down below, 1,890 kilograms. So how much would 5 gallons of water be? Got it? Just a way to simplify yourself. And this is so you had 500 gallons of water equals how much? I say that was kilograms. 1890? 1890 kilograms. We can do a ratio, can't we? For 5 gallons. 5 gallons to 500. What's 5 over 500? 0.01. Doesn't quite do it ratio-wise, but that gives us 0.01 times 1890, 18.9 kilograms, right? Of water. Maybe I better kind of do that differently. Let's do it as a better look here. I'll get some. So 1890 kilograms is the same as 500 gallons. We want to know what 5 gallons is. There it is. Equals 18.9 kilograms. That's a better way to present it. Well, we got it. Now we know the mass. Our latent heated vaporization only requires us to know, we know it's at 100 degrees centigrade, so we only need to know 2.258 megajoules per kilogram times the 18.9 kilograms. Whatever that comes out to be. I don't have that in front of me. It's about 19 times, about 20 times 2, about 100. There it is. About 43, approximately. 43 megajoules. But that's for only 5 gallons. So you can see the differences in energy required, and that's what this box is about. It takes more energy to boil the same volume away as it does to bring it from, like room conditions or even sub-room conditions, 45 degrees Fahrenheit up. 43 megajoules for 5 gallons. Let's take that for 500 gallons. Where'd that go? 737 megajoules. Okay. So that'd be for 5 gallons to bring 5 gallons to boil would be 100th of that. So it'd be 7.4 megajoules to bring 5 gallons to boil. But to boil 5 gallons of water away, it takes an additional 43 megajoules. And that's what this box is about. And they're dealing with different parameters. Okay? And this problem was presented, again, hey, let's get from English to metric, so we got a visual. And B, if you understand this box, you can do this problem pretty readily. And it's like the tables. You've got to take a little bit of time with some of these boxes. And some of them in particular go from one step to the other without showing it. And you can kind of get lost. So any questions on that?
I can't quite read.
Oh, I don't blame you.
Number on the left.
Oh, this guy?
Yeah.
Yeah, that's a real important number too. I shouldn't have wrote that so sloppy. Let's get it out of there. That's the latent heat of vaporization, or condensation in this case. Oops.
Oh,
Yeah, that's that 2.258, which we showed up here. Go on back. Where'd I go? Come on, dude. This thing sometimes when it takes a while to come back. There. That's the 2.258, which I tried to write there, didn't do a very good job of it. See you later.
See you later.
We're going to go through some test questions if you were interested. There it is.
I gotta get to another class.
Oh, hey, I understand.
I know the other one is.
Yikes. Good luck.
Oh, thank you.
2.258 megajoules per, that's supposed to be kilogram. Okay. That's the same, that's the latent heat of vaporization, or in the other direction, condensation. Okay. Well, let me close this one out, or at least pause it, and we'll get to another topic or two. Yeah, well, that's enough. What have we got, a half hour left? Yeah.
No, we're done at 2:30.
This is it? Oh my gosh, look what I've done. There are some test questions requiring open-ended answers or short word answers. You probably already witnessed that with your first exam, where the automatic grader might mark it wrong when it's really right, because you set it a little differently than the automatic. The automatic grader allows you to put several potential answers in there. So be patient with that, and it's a little bit of a thing when you go and you take an exam twice, but be patient with that. I think in your exam there were a fair number of open-ended questions, but they weren't all that bad. Again, use your text. When you go to take one of those exams, you guys are experienced with it. Allow yourself the full time. You may not need it, but make sure you've got the time to take the full time if you can. And do it enough time you got your chance to get back and do it again if you so wish. So.